Hello students, I hope you are doing well. If you are seeing this video, my request is to subscribe this channel and share this type of videos to your friends. Remember that knowledge only increases upon sharing, right? So don't forget to share these videos and definitely subscribe this channel. So being said that, we will move to today's question discussion. Today I have taken a question from gravitation chapter from the book Irodov. This is a nice question. I thought to share the solution with you. And after solving this question, I will provide you another similar type of question that is more interesting. And by using the concept of this question, you have to solve that one. Okay. So let's start with the first question from Irodov. It says a small body starts falling onto the sun from a distance equal to the radius of Earth's orbit. The initial velocity of the body is equal to 0 in the heliocentric reference frame. Heliocentric reference frame means here the reference frame where you can assume sun to be at rest. Making use of Kepler's law, find how long the body will be falling. So you need to use Kepler's law. Although this question seems to be very easy if you use simple mechanics equations, but try to solve it. If you can do it in that way also, you can find the accurate answer. Otherwise, you can also find the approximate result by using Kepler's law. So take your time, pause this video, and I can come back to see the solution. So students, I hope you have given a good try to this question. Let's come to the solution of this problem. So I have done here two different approaches to solve this question. So first I have written this exact. Exact means you can find the exact time by this method. What this method tells, it says that initially suppose this object was here and sun is here and the distance in between them is capital R, which is the radius of Earth's orbit. Right? So here you can see that this is the sun, this is the Earth's orbit. Earth moves in a circular orbit. So I can say that the time period of this orbit is 2 pi by root gm into r to the power 2 by 3, which is 365 days, we all know. Now in terms of this 365 days, we need to calculate how much time this body will take to fall onto the sun's surface. So I have taken that at any instant time t, the distance between the center of the sun and the point mass is x, and the speed of the particle towards the sun center is v. And how do we know the velocity v here? We can simply use the conservation of energy equation between this initial and this position. So initially the particle was at rest, and the particle is at a distance capital R from sun. So the potential energy, as we know that equation is minus gmm by R. So minus gmm by R is the potential energy of the sun particle system, and the kinetic energy is half m v square, which is 0. And here when the particle is at a distance x, the potential energy is minus gmm by x, and the kinetic energy is half m v square. So from here, if you modify, you will find the value of v in terms of x like this, and then you can write that v equal to minus of dx by dt. This minus sign is important because the distance x that decreases as time progresses, right? So I can write v is equal to minus of dx by dt, and that is equal to this one. So you can now take the dx in one side and dt in one side. After integration, you will find the time, and the x you will vary at t equal to 0. The x was capital R at t equal to 0, and at final time t, the x is small r. So if you do this integration, you will find your answer. But you can see that the integration is not easy to solve. You can try to solve it, and you can find the exact answer to the question. But the question itself says that don't do this, don't find the exact answer. The question says that find the approximate answer by using Kepler's law. So how we can use Kepler's law in this question? Let us try to understand that this particle is straightforward coming to the sun. But I can say that this straight line path, we can approximate that straight line path to be a highly elongated ellipse, right? The eccentricity of the ellipse is very large and it is a highly elongated ellipse, and sun is at one of the focus of that ellipse. Now we can apply Kepler's law, because we know that if a particle or planet moves in an elliptical path, the time period is 2 pi by under root gm into a to the power 3 by 2, where a is the semi-major axis. Now here we can say that the total distance from here to here we can calculate approximately to be r. Why? I can say that, look, this sun has a small radius than the radius of the orbit, that you can also assume. So I can assume sun to be a point mass only, right? So here this is the sun and this is the particle. The distance in between them is r, and I can assume this capital R plus small r, you can also say, that is the total 2a. From this point to this point, the total distance is 2a. And again, I can approximate this one as capital R is much greater than small r. So this total distance is r, and the semi-major axis is half of this total length, and that is r by 2. Now I will just put the value here, r by 2, and you can see that this is your result, and r to the power 3 by 2 divided by 2 to the power 3 by 2, which is 2 root 2. And I know that 2 pi by root gm r to the power 3 by 2 is basically 365 days, right? So your answer should be half of this time period. Why half? Because it only takes this path to come to the sun. Half of this time period is your actual time of the particle to fall on the sun, and that is 365 divided by 4 root 2 days. So that is the approximate answer of this question, right? I'm sure that you have got the solution. You have understood how I have approached this question, and if you have any doubt, you can definitely put those doubts in the comment box. Alright, so now with the concept that we have learned, I will give you another question, that is another interesting question. So you try to tackle with that question, take your time, and whatever concept you have learned here, try to apply in this question. This question says 6 particles are placed at rest at the corners of a regular hexagon of side length r. So find the time when they collide due to their mutual gravitational force. So as the particles are attracting with each other, so there will be an inward gravitational force to all the particles. You need to calculate the time when they will collide. Okay, so I hope you have given it a good try, and if you have got the correct answer by yourself, then definitely mention it in the comment box that how much time you have taken to solve this question. Let us go into the solution page. So the solution, before coming to the actual solution, let us try to understand what is happening to each and every particle. Look, this is the hexagon that I have drawn, and all the particles are at the corners of a regular hexagon. The side length of the regular hexagon is r, and let me concentrate on a single particle A. So at this instant, the particle is experiencing force by attractive force by all these 5 other particles, and the net force is what I have written here, right? The net force, you can see that this particle B will pull it by gmm by r square force, and I have taken a component along this line A to O. O is the center of this regular hexagon, and I'm sure that you can understand all the particles will experience force along the line joining between the particle and the center. So they will try to come towards the center, and interestingly, whenever they will try to do it, every time they will form a regular hexagon always, right? Because you can see that particles are symmetric, so the force on each of the particles are same, so every time they will move towards the center symmetrically, making a regular hexagon. So these side lengths will change of the regular hexagon obviously, but the angles of this force with this vertical line or with the line AO will not change. So let me take, when the particle is at this point, the hexagon has a side length r. What is the force on this particle A? So 2 into gmm by r square. Why I have multiplied with 2? Because this force and this force both are the same, and when I take the component, this is 60 degree, right? This angle is 60 degree. So cos 60 degree angle I have to take the component of these forces into half. That is why I have written. For this force, it's gmm by root 3r whole square. So this is 3r square, and this angle is 30 degrees, so cos 30 is root 3 by 2. Again I have multiplied it with 2 just because that these two forces are same and they will have the same effect along the line AO. And another particle is D. At D, so it will pull the particle A at gmm by 2r square. When I add these forces, I get this result. And I have taken gm square by r square common, and this is the result I have got. Now what I have done, I have taken this particle m along, and instead of these 5 isolated particles, I am saying that if I place a equivalent particle at the center O, then what will be the m equivalent, so that the equivalent mass also pulls this particle A with the same force. So I can modify this equation as gm by r square, because this AO distance is r. So gm by r square multiplied by whatever remaining term is there is the mass equivalent. You need to understand it, that instead of having 5 different particles pulling the particle A, I'm going to replace these 5 particles by a single m equivalent particle that is placed at the center O, so that the force remains intact. So in that way I can find that m equivalent is equal to this one. And why I have done that? Because now you can see that this question is very similar to the last one, when here is the sun and here is the particle that we were discussing in our last question. So here I have drawn that now this m equivalent is here and this small mass is here, and definitely this mass will come in a straight path, but we can always approximate that straight path to be a highly elliptical path, right? And so the time taken by the particle to come from here to here is 2 pi by root gm into a to the power 3 by 2, where a is the semi-major axis of this highly elliptical path. And what is that semi-major axis? I know that this two distance is r, the distance between small m and capital M is capital R, and that is nothing but 2a. So a is equal to r by 2. When I put the value here, I got my answer. Only thing is, here you have to replace capital M by this m equivalent. Then you will find your answer, right? Because this capital M is the mass m equivalent that I have got from here. So I hope you like this question, and you have understood the solution completely. And anytime if you find this type of question, that what is the time, then you can think about this solution. I'm not saying that it will give you the accurate result, but yes, with this upon seeing the options, you can always take a decision that whether you have to go for the accurate answer by integrating that dx by dt function, or you can apply Kepler's law and find a simplified approximate result. So that's all for today. See you in the next video.